The lithium-air battery, Li-air for short, is a metal-air battery chemistry that uses oxidation of lithium at the anode and reduction of oxygen at the cathode to induce a current flow. Originally proposed in the 1970s as a possible power source for battery electric vehicles, Li-air batteries recaptured scientific interest in the late 2000s due to advances in materials technology and an increasing demand for renewable energy sources. The major appeal of the Li-air battery is its extremely high specific energy, a measure of the amount of energy a battery can store for a given weight. A lithium-air battery has an energy density comparable to gasoline. Li-air batteries gain this advantage in specific energy since they use ambient oxygen instead of storing an oxidizer internally. Significant advances in multiple fields are necessary to develop a commercial implementation. Four approaches are active: aprotic, aqueous, solid-state and mixed aqueous. Aprotic metal-air batteries, specifically zinc-air, have received attention due to potentially high energy densities. The theoretical specific energy densities for metal-air batteries are higher than for ion-based approaches. Lithium-air batteries can theoretically achieve 3,840 mAh per gram. A major driver is the automotive sector. The energy density of gasoline is approximately 13 kWh per kilogram, which corresponds to 1.7 kWh per kilogram of energy provided to the wheels after losses. Theoretically, lithium-air can achieve 12 kWh per kilogram excluding the oxygen mass and deliver the same 1.7 kWh per kilogram to the wheels. After losses from overpotentials, other cell components and battery pack auxiliaries, given the much higher efficiency of electric motors, lithium-air batteries have the potential of 5 to 15 times the specific energy of current lithium-ion batteries. History. Lithium first drew attention in the 1970s. The first commercial lithium cells emerged during the 1990s. In the mid-1990s, Kajikalayalem, Abraham and co-workers demonstrated the first non-aqueous Li-air battery with the use of a Li anode, a porous carbon cathode, and a gel polymer electrolyte membrane that served as both the separator and ion transporting medium. The Li-ion conducting gel polymer electrolytes were based on polyacrylonitrile and polyvinylidene fluoride. Operation. Although details vary by battery design, in general, lithium ions move between the anode and the cathode sides across the electrolyte. Under discharge, electrons follow the external circuit to do electric work and the lithium ions migrate across the electrolyte. During charge, the lithium metal plates onto the anode, freeing O2 at the cathode. Anode lithium metal is the typical anode choice. At the anode, electrochemical potential forces the lithium metal to give off electrons via oxidation. The half reaction is Li E-. Lithium has high specific capacity compared with other metal-air battery materials. Several issues affect such cells. Upon charging, discharging in aprotic cells, layers of lithium salts precipitate onto the anode, eventually covering it and creating a barrier between the lithium and electrolyte. This barrier initially prevents corrosion, but eventually inhibits the reaction kinetics between the anode and the electrolyte. This chemical change of the solid electrolyte interface results in varying chemical composition across the surface, causing the current to vary from point to point. The uneven current distribution furthers branching dendrite growth and typically leads to a short circuit between the anode and cathode. In aqueous cells, problems at the SEI stem from the high reactivity of lithium metal with water. Several approaches have been taken to overcome problems at the SEI. Formation of a Li-ion protective layer using di- and tri-block copolymer electrolytes. According to CO, Inc., such electrolytes combine the mechanical stability of the hard polymer segment with the high ionic conductivity of the soft polymer, lithium salt. Mixture. The hardness inhibits dendrite shorts via mechanical blocking. Li-ion conducting glass or glass ceramic materials are readily reduced by lithium metal, and therefore a thin film of a stable lithium conducting material, such as Li3P or Li3N, can be inserted between the ceramic and metal. This ceramic-based SEI inhibits the formation of dendrites and protects the lithium metal from atmospheric contamination. Cathode and electrolyte. At the cathode during charge, oxygen donates electrons to the lithium via reduction. Mesoporous carbon has been used as a cathode substrate with metal catalysts that enhance reduction kinetics and increase the cathode-specific capacity. Manganese, cobalt, ruthenium, platinum, silver, or a mixture of cobalt and manganese are under consideration as metal catalysts. Under some circumstances, manganese-catalyzed cathodes performed best. With a specific capacity of 3137 mAh per gram, carbon and cobalt-catalyzed cathodes performed second best, with a specific capacity of 2414 mAh per gram carbon. Based on the first Poor-scale modeling of lithium-air batteries, the microstructure of the cathode significantly affects battery capacity in both non-Poor blocking and Poor blocking regimes. Li-air cell performance is limited by the efficiency of reaction at the cathode because most of the voltage drop occurs there. Multiple battery chemistries have been assessed, distinguished by electrolyte. This discussion focuses on aprotic and aqueous electrolytes as the solid-state electrochemistry is not well understood. In a cell with an aprotic electrolyte, lithium oxides are produced through reduction at the cathode. Li++, E- O2 plus asterisk Li-O2 asterisk Li++ E- Li-O2 asterisk Li2O2 asterisk square asterisk denotes a surface site on Li2O2 where growth proceeds, which is essentially a neutral Li vacancy in the Li2O2 surface. Lithium oxides are insoluble in aprotic electrolytes, which leads to cathode clogging. In a cell with an aqueous electrolyte, the reduction at the cathode can also produce lithium hydroxide. Acidic electrolyte 2Li plus 1/2 O2 plus 2H plus 2Li plus H2O. Conjugate base is involved in the reaction. The theoretical maximal Li-air cell specific energy and Li-air cell energy density is 1400 Wh per kilogram and 1680 Wh L, respectively. Alkaline aqueous electrolyte 2Li plus 1/2 O2 plus H2O2 LiOH. Water molecules are involved in the redox reactions at the air cathode. The theoretical maximal Li-air cell specific energy and Li-air cell energy density is 1300 Wh per kilogram and 1520 Wh L, respectively. The development of new cathode materials must account for the accommodation of substantial amounts of Li-O2, Li2O2 and/or LiOH without causing the cathode pores to block, and employ suitable catalysts to make the electrochemical reactions energetically practical. Dual-pore system materials offer the most promising energy capacity. The first pore system serves as an oxidation product store. The second pore system serves as oxygen transport. Design. Cathode AMNO2 nanowire array cathode augmented by a genetically modified M13 virus offers 2 to 3 times the energy density of 2015 lithium-ion batteries. The virus increased the size of the nanowire array, which is about 80 nanometers across. The resulting wires had a spiked surface. Spikes create more surface area to host reaction sites. The viral process creates a cross-linked 3D structure, rather than isolated wires, stabilizing the electrode. The viral process is water-based and takes place at room temperature. Electrolyte efforts in Li-air batteries have focused on 4 different chemical designs. All the designs have distinct advantages and significant technical challenges. Aprotic. Most effort involved aprotic materials, which consist of a lithium metal anode, a liquid organic electrolyte and a porous carbon cathode. Electrolytes can be made of any organic capable of solvating lithium salts such as LiPF6, LiASF6, Lin2, and Lisa3CF3, but typically consisted of carbonates, ethers and esters. The carbon cathode is usually made of a high surface area carbon material with a nanostructured metal oxide catalyst. A major advantage is the spontaneous formation of a barrier between anode and electrolyte that protects the lithium metal from further reaction with the electrolyte. Although rechargeable, the Li2O2 produced at the cathode is generally insoluble in the organic electrolyte, leading to buildup along the cathode-electrolyte interface. This makes cathodes in aprotic batteries prone to clogging and volume expansion that progressively reduces conductivity and degrades battery performance. Another issue is that organic electrolytes are flammable and can ignite if the cell is damaged. Aqueous. An aqueous Li-air battery consists of a lithium metal anode, an aqueous electrolyte and a porous carbon cathode. The aqueous electrolyte combines lithium salts dissolved in water. It avoids the issue of cathode clogging because the reaction products are water-soluble. The aqueous design has a higher practical discharge potential than its aprotic counterpart. However, lithium metal reacts violently with water and thus the aqueous design requires a solid electrolyte interface between the lithium and electrolyte. Commonly, a lithium-conducting ceramic or glass is used, but conductivities are generally low. Mixed aqueous, aprotic. The aqueous, aprotic or mixed Li-air battery design attempts to unite advantages of the aprotic and aqueous battery designs. The common feature of hybrid designs is a two-part electrolyte connected by a lithium-conducting membrane. The anode abuts the aprotic side while the cathode is in contact with the aqueous side. A lithium-conducting ceramic is typically employed as the membrane joining the two electrolytes. In 2015, researchers announced a design that used highly porous form of graphene for the anode, an electrolyte of lithium bisulfonylimide dimethoxyethane with added water and lithium iodide for use as a mediator. The electrolyte produces lithium hydroxide at the cathode instead of lithium peroxide. The result offered energy efficiency of 93% and cycled more than 2,000 times with little impact on output. However, the design required pure oxygen to function, rather than ambient air. Solid-state. The solid-state battery design is attractive from a safety standpoint, eliminating the possibility of ignition from rupture. Current solid-state Li-air batteries use a lithium anode, a ceramic, glass, or glass-ceramic electrolyte, and a porous carbon cathode. The anode and cathode are typically separated from the electrolyte by polymer ceramic composites that enhance charge transfer at the anode and electrochemically couple the cathode to the electrolyte. The polymer ceramic composites reduce overall impedance. The main drawback of the solid-state battery design is the low conductivity of most glass ceramic electrolytes. The ionic conductivity of current lithium fast-ion conductors is still lower than liquid electrolyte alternatives. Challenges. As of 2013, many challenges confronted designers of Li-air batteries. Cathode. Most of the current limitations in Li-air battery development are at the cathode, which is also the source of its potential advantages. Incomplete discharge due to blockage of the porous carbon cathode with discharge products such as lithium peroxide is the most serious. The effect of pore size and pore size distribution remains poorly understood. Catalysts have shown promise in creating preferential nucleation of Li2O2 over Li2O, which is irreversible with respect to lithium. Atmospheric oxygen must be present at the cathode, but contaminants such as water vapor can damage it. Anode. The main challenge in anode development is preventing the anode from reacting with the electrolyte. Alternatives include new electrolyte materials or redesigning the interface between electrolyte and anode. Dendritic lithium deposits can decrease energy capacity or trigger a short circuit. Electrochemical in current cell designs, the charge over potential is much higher than the discharge over potential. Significant charge over potential indicates the presence of secondary reactions. As a result, electrical efficiency is only around 65%. Catalysts such as MnO2Co, PT&O can potentially reduce the overpotentials, but the effect is poorly understood. Several catalysts improve cathode performance, notably MnO2. The mechanism of improvement is unknown, but may alter the structure of the oxide deposits. Significant drops in cell capacity with increasing discharge rates are another issue. The decrease in cell capacity is attributed to kinetic charge transfer limitations. Since the anodic reaction occurs very quickly, the charge transfer limitations are thought to occur at the cathode. Stability. Long-term battery operation requires chemical stability of all cell components. Current cell designs show poor resistance to oxidation by reaction products and intermediates. Many aqueous electrolytes are volatile and can evaporate over time. Applications. Vehicles. Li-air cells feature high specific and volumetric energy density, comparable to petrol. Electric motors provide high efficiency, 95% compared to 35% for an internal combustion engine. Thus, Li-air cells could offer range equivalent to today's vehicles with a battery pack one-third the size of standard fuel tanks. The reduced vehicle weight creates a virtuous circle in that the motor size can be reduced, further reducing weight and battery requirements. Grid backup. In 2014, researchers announced a hybrid solar cell battery. Up to 20% of the energy produced by conventional solar cells is lost as it travels to and charges a battery. The hybrid stores nearly 100% of the energy produced. The first version of the hybrid used a potassium-air battery. It offered higher energy density than conventional Li-ion batteries, was less expensive and avoided toxic byproducts. The latest device essentially substituted lithium for potassium. The solar cell used a mesh made from microscopic rods of titanium dioxide to allow the required oxygen to pass through. Captured sunlight produced electrons that decompose lithium peroxide into lithium ions, thereby charging the battery. During discharge, oxygen from air replenished the lithium peroxide.